Hello, everyone. I hope you hear and you see me. I'm Danila. So today I'm going to talk about how to make the most out of your compiler. First of all, who am I? I am a software engineer at Google. I work in data pipeline and efficiency and infrastructure. It's map reviews and so on. In the past, I was working at core search engine at Yandex, one of the most popular search engine in Russia. I'm a ClickHouse contributor concerning efficiency and infrastructure. I'm C++ library and compiler contributor from time to time, and I teach C++ in universities. Some disclaimer, this talk is going to be opinionated, maybe like a little bit following the fashion, but these are my opinions and the opinions the results that I saw from different projects. Also, I'll take all questions at the end, so we'll have 7 to 10 minutes. All right, let's start. There is a rumor going on among engineers who write C++ that you should trust your compiler. That's true, that's reasonable. I mean, you start learning C++ and you should compile your program in order to execute it, and you should trust this process. Compilers are smart, that's also true. Compilers can do some weird optimizations, and you just you can build for debugging, for optimization, and so on. And they do some really complex and interesting stuff. Don't over-optimize. Don't have any, sometimes people call it, don't do any premature optimizations. That's also true. I mean, make it, first of all, like work, then make it fast. And biggest rumor that C++ is fast. Probably it's one of the fastest language on the market. Today, I'm going to debunk all 4 points in some way or another. And let's start with actually the compiler and why you should trust it. Overall, I believe that one of the biggest problems that engineers have when they write C++ is that after thousands of hours of practicing, they still don't understand how to write a barely working compiler. So, for example, I don't know, if you have some line of code that I present, probably you need some time to process it. And if you don't, congratulations, like you are probably like a very good C++ expert. And on the other hand, we prioritize freedom. So we don't have any centralized build system or centralized compiler. And we explicitly say that and mean that people should choose C++ to control. However, most engineers don't have any idea what's happening behind this black box of like named compiler. Still, like you choose probably if you write C++, you have a reason to do that. This reason may be speed, or like expressing as history, knowledge, hiring, ecosystem, tooling, whatever. And some of this you can control. For example, you can hire good engineers that have long experience of learning and doing C++. But 2 things that I'm going to talk today more is about speed and tooling. So what's going to happen on the compiler level. And we all know our best and beloved compilers that you use. I believe like compiler market is not very big. Maybe dozens of them exist, which I know of. Most popular, I believe, are GCC, LLVM, MSVC, Intel. There are some others for sure. For example, IBM compiler. But today I'm going to focus on the most popular ones as it covers more engineers who do their job. I'm going to focus more on LLVM and Clang. Most points will be available for GCC. Some points are also present for MSVC, and so I believe I'll try to be as generic as possible. But on the other hand, I'll try to suggest something very specific when it comes down to like specific options or something like that. All right, and yes, LLVM has around 1,800 options to configure. And that's actually blew my mind when I tried to dump all of them. And that's true, you can customize your compiler as much as you want, or fine tune it. Also, like there is, like you can configure a compiler. On the other hand, there are recent breakthroughs. I believe that quite quite good to know. For example, SIMD JSON is the library that was written not so long ago, maybe 2 to 3 years, and it parses JSON and does nothing else. So it's really good in parsing. And you can see that the closest competitor is like 2 times slower than this library. And the most popular library for JSON is like JSON for modern C++ is like parsing at a speed of 100 megs when SIMD JSON goes to 3 gigs. But this is the same C++, same set of inputs, same compilers, and what's actually different? Well, like good answer. The truth is like it's really complicated, but let's briefly discuss some moments and then we dive into them. First of all, like it's called SIMD JSON. It uses SIMD instructions, which stand for single instruction, multiple data, for example, to work with 16, 32, or 64 bytes at the same time. And SIMD JSON is full of that thing. So like it uses like this weird intrinsics and does a good job providing like of processing more data in one instruction. Also, like this library uses lots of compiler options and compiler extensions. For example, it uses sometimes the targets of SSE 4.2 and other instruction sets and so on. Well, probably the most significant part is that it was put like hundreds of hours into that by providing the best possible performance. This picture is not very relevant. You should not read it very carefully, but it just shows that the code generation is very pipelined. It's very good for processing like really wide registers. So lots of hours were put into optimizing like parsing JSON. So, and the point that I want to make here is that don't blame your compiler for being slow. They will not generate best possible code for you for various reasons, because it's sometimes hard. The compilers also have trade-offs. It's like, I don't know, really hard to compute the fastest program that solves your problem, if it's even possible. Also, one point that might be relevant, but still I want to point this, that there is a chance your code base will grow and you won't notice. So for example, if you build a library or a project, you write code, after a year, you probably still write code and so on. That means that like simple tasks like parsing JSON can be optimized 2 to 30 times. And probably if you write code, you have some potential for optimizations due to this, I don't know, SIMD instructions or compiler options and so on. And there is likely a huge gap. You won't control this. Like in this sense, you should trust your compiler. However, I'm going to show you some options that can fine tune it to get a little bit more out of this mess, like out of this, I know, hundreds of thousands lines of code. And I split this into 4 parts, and 3 of them are forgotten stories. One is not very forgotten, but we'll talk about it. So first forgotten story that some engineers just don't understand for some reason or don't pay attention too much is the visibility. Here is the simplest code. You have a library, .h. There are 2 functions, for and bar. There is library.cc. The implementations of bar. Everything seems normal. You compile library.cc and then link with, for example, main.cc. And main.cc just includes library and somewhere calls foo and bar. And the question from me is whether the calls can be interchanged. So first we call bar and then foo. Can compiler actually is compiler allowed to do that? And pretty straightforwardly, I believe the answer is no, that it cannot, like if it has foo and then bar, like it cannot call first bar and then foo, even if it's, for example, beneficial for performance. Because, for example, you have global memory and you can lock some statements. This is a side effect. You write to some file or to some std out, and you just cannot mess with this ordering. But for compilers, it actually may be like even beneficial. So compilers just don't see it, but I mean, they can. If they knew something about foo and bar better, probably they can interchange or inline some pieces of code and so on. To increase the visibility to compiler, yes, you can write into headers, and we have actually infrastructure in C++ for that. So you can write the inline keyword upon the function, or if the function is templated, it's inlined by default. But my suggestion, please don't do that very often. So it really, really, really increases the the compile times. If you include headers in multiple times, this function is going to be duplicated in each source file, and your compile times just become significantly bigger. Well, compile times are important as well as performance is important. So how should we balance it? There is a reasonable question that yes, if we don't write in headers, we lose performance. That's true. That actually happens in practice. I say always that productivity is important. Please don't ignore that point. What I want to suggest is the middle ground for that. So it's called link time optimizations. And so some of you may heard this, but that's still a very important part. So what's link time optimization itself? So you have 3 stages of compilation. During C++, it's like preprocessor, the compilation itself, and the linkage stage. And link time optimizations happen like on the 3rd stage, where actually all code is visible, and LTO sees all program. So it, for example, it will see that foo and bar are compiled in library.cc from my example, and will try to optimize to inline them probably into main. However, LTO, if it sees all program, it may not be very scalable if your code base is huge. So for example, LLVM provides a technology called thin LTO. So, and the main idea behind that is that it generates actually not the libraries, but it generates the intermediate representation. We will talk later a little bit about it. It provides some summaries of actually all potential optimizations that can be done. For example, if the function is big, there is no point in inlining it. But if the function is small, probably it can be inlined. And by removing this, I don't know, big functions or unnecessary information, we increase scalability. Yes, we lose some optimizations which can be potentially be applied in simple LTO case, but thin LTO still tries to get this middle ground between scalability for large code bases or even like mildly big code bases and compile times. So yeah, flags for a compiler -f LTO like in GCC and Clang, and FLTO equals thing. It's available only in LLVM. What we actually observed, so we observed the performance gains from around 0 to 10%. In Google, we saw like on average 3-4. Like it depends on workload, but still like it's not trivial amount of like CPU cycles. Okay, so possible workflow for you to develop, like link time optimization all increases the compile time. That's true. However, like you can have usual builds without any link time optimizations, release builds with link time optimizations. In that case, you will gain all the performance gains, and you will have better opportunity to iterate over your code by not blowing the compile times. Usual LTO may be unscalable, so that's true. For example, we probably saw that LTO starts to ooming, so not enough memory, from 50 to 100,000 lines of code. So be careful if your code base grows. So LTO may not be the best solution for you. So thin LTO like provides better middle ground. Example, this is an open source analytics database. ClickHouse cares about performance a lot, has lots of SIMD like processing and so on. So one of the key features of ClickHouse is performance. It has 400,000 lines of code. We tried LTO a couple of years ago. We got 2% performance gains. It still was not at the pace of GCC, but actually eventually we removed, like Clang became faster than GCC. And we removed GCC from it, but FLTO just didn't finish, like simple LTO didn't finish. Caveats. You can argue. You can argue that yes, we can have the builds when you iterate, you test, and release builds, but you don't test what you really build. That's a valid point. From my experience, as for example at Google, we haven't seen any problems for thousands of targets. And what actually helped, sanitizer usage helps. So it tries to find all undefined behavior that can be exploitable, and integration testing helps. So please, if you do some changes into your build, just try to have some integration testing, or as an alternative, try to build once a day, for example, the release build, and then test all of your test suite. So that also can work. All right, so more visibility to the compiler opens more optimizations, and these are not non-trivial ones. Next story, it's not actually, it's not the story that people forget, but still they have some confusion about it. So for example, like there are optimization levels, -0, -1, -2, -3, -fast. So what do they actually mean? In order to understand what they actually mean, let's dive a little bit into the architecture of the compilers. Fortunately, GCC and LVM in some sense have similar architectures. Like roughly there are three parts. So front end is like understanding the semantics of C++ and like converting into the IR. IR is intermediate representation of the which is, I know, has all good properties. For example, static single assignment, like no variable can be assigned twice. And like lots of theory behind that is done, like why it is better and so on. So compiler people know better why IR is good for compilers. So middle end is like the stage where the optimizations over IR happen, or like sometimes compiler people like to call them canonicalizations more, but optimizations probably is a little bit like more popular word. And understandable ones. And the backend is actually the real code gen, how we translate the optimized IR into the architectural assembly, and probably even apply a couple more optimizations that are specific for the microarchitecture that we do, that we build for. For example, Clang has like very strict like split into three stages. Like for example, like it tries to understand the semantics of C++, checks for all errors. Then it goes into the optimizer. Optimizer consists of so-called passes. Passes, like there are a couple of hundreds passes, I believe now in LLVM, which like transform IR into a better optimized way. Then there is the backend stuff, which also has a couple of like several passes for micro architectural optimizations, and then it translates into binary. And GCC has similar, so it takes the text input, translates into AST, then it translates into generic AST, then it translates to Gimpel, which is like intermediate representation. A couple of more stages that I don't want to dive into, but like you still need to understand that there are passes. Like these passes are probably one of the most important are parts of the compiler, just like what makes C++ fast, or like actually like any language fast. So middle end, yes, these optimizations happen over the intermediate representation. They consist of several stages, mostly like cleanup, canonicalization, simplification, optimization, target-specific optimizations. For example, inst combine is the pass which is responsible for instruction combine, like dead code elimination, wherever you can think of any optimization that can be applied. Probably a couple of passes that are not quite so popular, like for example, inliner. It tries to understand which functions should be like inlined into the IR, and loop optimization. So how do we rotate loops or delete loops or unroll loops or vectorize loops and so on. So these are quite important. And basically -0, -1, and so on mean that like the level of like passes that you actually want in your in your build. So for example, -0, almost no passes, probably a couple of them, just some very simple ones. -1 includes some passes, -2 includes like most passes, -3 includes all passes. I believe the biggest differences between -0, -1, then -1, -2, but difference between 2 and 3 levels are not very big. We'll see a little bit later, but what I mean. -fast actually is quite dangerous, and it includes -3 and fast math plus some weird more flags, which I don't want to mention right now. So fast math, for example, thinks that your floating point arithmetic is cumulative, that your floating point arithmetic is finite, and all this stuff, which probably can be dangerous in general case. So if you use -fast, be careful. So really be careful. So for example, -3 in GCC includes several options, and probably the most important ones are the loop unrolling, and that's the biggest difference between -2 and -3 in GCC. So, and yeah, fast math sets some flags with unsafe math optimization flags, and when I see the word unsafe, I become a little bit suspicious, like whether I actually need it. So, for example, I haven't seen that -fast being deployed to some really big projects because of these concerns, but it can be useful in some cases. Good news, loop vectorization is enabled by default in -2 from GCC 12, yet GCC 12 is not yet released. So we'll see if it's going to be rolled back or not. No, I hope not. Yes, let's open our best site called Godbolt, and you can see GCC on the left is the code which basically sums the vector, nothing more, vector of integers, and -2 in GCC just does some very simple loop, and in -3 it does really stuff that probably compiler engineers know better or what they mean. So that's the biggest difference in GCC. LLVM with -3 is not very much different from -2. It includes a couple of passes, and a couple of option adjustments and loop unswitching and so on. So in LLVM, -2, -3 are almost the same, like from my experience. Yeah, and one example that I can show you just for the record, like on the left, there is some weird code that computes the number of ones in the 32-bit integer, and client with -3 understands that it's a pop count instruction. However, with -2, it doesn't understand it. And the pass that's responsible for that, I believe, called aggressive inst combine. Yes, this is aggressive inst combine pass. So it's just purely for an example. My point, please use -0-g J's for debug information for debugging purposes, use -3 for optimization purposes. Sometimes I hear that -0 is too slow for debugging. That's also can be true, and please make sure that, I mean, just it's fine. It's okay if it's too slow. My suggestion will be to use these 3 options: -1, fno mid frame pointer, fno optimized sibling calls. What do they actually mean? -1 does include some optimizations, but it has lower restrictions on inliner and so on. Fno mid frame pointer is the option that saves the base pointer and provides better stack traces. Fno optimized sibling calls removes tail call elimination, and debuggers are less confused that this function is deleted. And for example, if you have a breakpoint to some line of code, it may never be hit because it was tail call optimized, and -1 includes tail call optimization. There is a flag called -OG, so optimized debugging experience. I believe it works nicely only in GCC. So for LLVM, this is not the case. So if you use GCC, probably -OG is already good for debugging. What else can I tell you about passes? I know a couple of years ago, I had a request from a friend. They were suspecting compiler bug because everything was working in debug mode, sanitizers were passing, and like the only place that was buggy is the release mode. And first of all, I thought that some undefined behavior for sure, because I mean most bugs are in software rather than in compilers. But what I actually suggested, if they struggle and if they think that this is a bug in optimizers, there is so-called optimization bisecting. So you can have all passes. There are a couple hundreds of them, and you just can bisect to the pass which actually does the worst job, or vice versa. For example, if you want to understand which pass optimizes your code, and for example, to debug it, to look into it from the source code of the compiler. Option is called like that, -m_LLVM -opt -bisect -limit equals some number. I don't know any of this infrastructure in GCC, but if you know, please let me know. So I used several times bisecting for debugging purposes or for understanding why optimization applies or not. And yes, friend actually found the pass that they were running. It was called toAddress instruction pass. I have no idea what that actually does, but there is some documentation for that. And yeah, some very long function, which is probably not very important. It really was a bug. And we were able to find it in pretty short time. So by understanding the architectural level of the compilers and how you can control your passes and how you can enable some of them, disable some of them, and so on. Another request that I had some time ago is, for example, one of the developer of ClickHouse changed the operator less to operator not equal in some for loop, and they got plus 30% of loop performance, which was reflected in some real query. And I asked them, like, are they sure that this is the only change? They were quite sure, but these were almost raw pointers. So really, this is a very simple code for the compiler actually to vectorize. However, this was not the case. What I suggested to a friend, LLVM, for example, has analysis options for some passes, and they can provide diagnosis of like whether the pass, what is the outcome of this optimization of this piece of code. And yes, LLVM actually told us that loop not vectorized could not determine number of loop iterations. And for some reason, it was not happening when you write the operator not equal. This was really, really suspicious. The truth behind that is quite complicated. What actually happened? So this was a boost iterator. And for example, as you can see for boost iterator facade relation, like the operators equal or not equal were like using one macro, and for random access relation, they were using another macro. And I believe the problem was that the second macro generated lots of code. So this code, this macro was expanded into something like that. I omitted some parts of it. So, and it was just hard for the compiler to probably hit some limit, which we don't understand. But this actually happened, and we were quite happy to remove boost iterator and just go with raw pointers and have 30% performance win. Forgotten story, which I also like, maybe not so forgotten, but I see that users don't exploit that as much as they should. It's the microarchitecture. And microarchitecture is a good thing because, I mean, hardware evolves, new instructions are added, caches and cache lines also grow. So why not using all this cool stuff? And disclaimer. So what I'm going to tell next, it purely depends on the hardware you run. I'll try to provide some summary of what's available in cloud or in data centers, which I was developing for, and so on. And then we will talk about some generic advice on that. x86, which is probably one of the most important or still architecture or microarchitecture for cloud processing. And if I split them in 2 to 3 eras. One era, I call it Westmere era. Westmere is the name of the processor, which was developed in 2010. And this processor actually was the last processor to update almost the last processor to update all 16-byte instructions. For example, it provided SSE 4.2, and let's briefly discuss. So SSE instruction sets are like SIMD instructions which operate with 16 bytes. Carry-less multiplication, or PCL-mul, is like the multiplication of Galois fields. It's beneficial for CRC checksumming and for erasure codes. AES is advanced encryption set, which is used like highly in some infrastructure like OpenSSL and so on. CX16 is log-free 16-byte atomics. Pop count is the pop count instruction. So Westmere era was the last one to have all these 16-byte instructions. And then only in 2013 we have Haswell processors, which introduced wider 32-byte registers and bit manipulation instructions, which can operate actually on registers of smaller size, but they were added only in Haswell. And FMA, it's like multiply addition, A plus equals B times C. It's good for some dot product multiplication, I believe. Okay, so also, I mean, you can argue we have AVX 512 in recent processors. That's also true. And I want to have a note on that why just don't we default to AVX, AVX2, AVX 512 by default? So AVX 512 is pretty recent, and actually the problems came even from AVX2. So if you share, for example, AVX code with non-AVX, you have CPU downclocking. If some binary that surrounds you is running only SSE and you're running AVX, there can be problems. If you use heavy AVX instructions, for example, some floating point instructions, then it's also CPU downclocking. And when your CPU has less frequency, your program becomes slower. And that behavior was observed on all processors, like before, like Skylake and including Skylake, or even Cascade Lake, as I remember, from Ice Lake. But Ice Lake was 2 to 3 years ago, as I remember. It becomes better. So only 2 to 3 years ago, we actually have stable AVX2 instruction, which doesn't harm overall CPU performance. That's why, for example, AVX, AVX2, AVX 512 is not very widely used by default. And next slide, spoiler, next slide is going to be like absolutely subjective opinionated, comes from my experience, but let's see what you can do with your architecture. So you start with your architecture. Let's first discuss the x86 one. If you have some hardware that's before 2010, I would consider like the question for you, can you throw it away? If you can, just throw it away and replace it with something more modern. If you cannot, that's also a possibility. For example, you develop browser or you develop library that's going to be shipped to people that with any hardware, very wide hardware. So just don't touch anything then. If you're sure that your processors are like at least 18 years, like newer than 18 years long, use options like SSE 4.2, AES, PCL-mul, CX16, pop count. If you have something between Haswell and Cascade Lake, for example, if you can prove that all your processors that you run hardware are at least Haswell, try to use the options so-called march equal Haswell and prefer vector width 1 to 8. And this option, prefer vector width, actually disallows compiler to use 32-byte instructions, which is a good thing not to downclock your CPU. And if you have something from Ice Lake, yeah, I see no reasons not to include AVX2, FMA, BMI, and probably you can think of AX512, but be careful, not all processors support AVX512. For example, some AMD ones do not, and so be careful with that. If you have some, like on other architectures, it's a little bit simpler. For example, for ARM, if you have, I don't know any data for ARM v7 actually, but probably it's the same for like ARM v8 and ARM v9. Use the option like march ARM version plus like some extensions, which some of them are by default, but I see actually like most of them being available in processors. For PowerPC, also if you have something older than P8, Power 8, just probably you know what you do. But if you have P8, P9, or P10, just use MCPU power, and Altivec is the SIMD for power processors. So it's pretty simple. For x86, it becomes complicated because of some effects which were not quite desired. All right, point of all this is that compilers assume really old hardware. For example, GCC included now defaults to Core 2, which is 2006. And probably there's a high chance that you develop code for much more modern hardware than this one. And just exploit that, that's perfectly fine. I also want to note that sometimes I hear from engineers I can use the native architecture like for compiling, and I highly don't recommend this because native architecture is architecture where you build, and if you don't have the control over your hardware or you don't know which processors you run, then it may become really costly because of illegal instructions. If you can control the hardware and you know you're very homogeneous, then probably it's fine, but still just use a march equal hardware you run on. So native is a dangerous option, be careful with that, and probably try to avoid it. Okay, I was talking a lot about micro architecture and all these new instructions, and these instructions are not very commonly used. And I believe that if you write code in C++, most of you just don't write this in SIMD. And the valid question you can ask, why would you want that? I would say that third-party libraries, really core libraries require that. For example, SIMD JSON has this division between Westmere and Haswell. If you have SSE 4.2, you have better implementation. If you have Haswell AVX2, you have even better implementation. And fallback is going to be slower than that. So, and probably you don't want to waste cycles in JSON parsing, and that's just a reasonable approach. For example, Hyperscan is the library for fast regexp search, and it also actually has even more splits. So it requires minimum SSE3, but it has SSE 4.2 division, pop count instruction, BMI, BMI2, IVX2. Some base 44 libraries also require AVX, AVX2 to get the maximum performance. ZSTD compression algorithm that is very commonly used right now requires BMI2 for exploiting that and being fast. Google's compression library, Snappy or Zippy, requires, it does not require, it just fallbacks to a non-optimized version if it doesn't have BMI2, for example. Yandex, where I worked, also has the library called FastOps, which is for fast mathematical operations. It also has this division. OpenSSL has a division. So I believe almost all core libraries right now that do care about performance, they really try to exploit these new instructions in some way, and it's their job. And what's required from you is just to allow them to do their job. The only thing you can do is just to adjust your hardware which you actually use. and options. All right, next forgotten story, which I kinda hear from many people, like not from many people, it's function inlining. So function inlining is the real inlining where you have a function and you try to inline so that you don't have any epilogue or prologue into the assembly. And my observation that generally inlining increases performance. For example, thin LTO tries to get all these small functions and inline them so you don't waste any cycles. Like probably the real truth is that if you inline really, really hard, then your code is impossible to optimize, impossible to find patterns, and it just becomes slower. And so this is like a U-shaped thing. So if you don't inline anything, you're slow. If you inline something very good, you're fast. But if you inline everything, you're also slow. So this is optimum that is pretty hard to find. Function inlining in compilers, as I understand, is a cost-based model. So it tries to compute some value, like tries to understand function, how what's inside, how expensive it is, and so on. And if it's not expensive, or if it has some good properties, for example, it can inline first couple of lines of code that checks for some errors and so on. It just inlines. So, and there is a threshold by which it inlines function or not. And yes, as I said, you cannot inline everything. That's a trade-off between compile time and the runtime. And sometimes inlining is bad. If you inline too much, instruction cache may grow, or like compiler may not understand what you actually mean. LLVM has this option for inline threshold. It's called -mllvm -inline -threshold equals to some number. Default is 225. This default is pretty good. And the truth is, if you increase that default, compile times grow. If you decrease that threshold, compiles time fasten. And disclaimer: inlining increases your build size, as I said, because you inline more, and now before that you can reference to one piece of code. Now if you inline it to every single function that uses it, so it increases the build size. Compile time also increases. That's a trade-off between performance and compile times. And for example, I tried to use it in several open source projects. And for example, this one of them, inline threshold equals to 2000, increased the compile time by 7 minutes from 30 to 37, as I remember. Inline threshold 500 increased from 30 to 33, and they increased build size by 30 and 10% respectively, as I remember. But they increased performance. They genuinely increased performance by 4 and 2%. And that thing is just, on one hand, that's a compiler issue. Compiler should better understand what to inline, what not. On the other hand, that's a pretty cheap performance gain. Just increase the inline threshold, you get better performance. So let me actually show one funny example that some engineers also think are good to share. This is a gold-bold link where I have two functions. I have function that inline stuff that is marked inline, and the other function is not inline. Generally, inline function is not about inlining. So it's not about function inlining. However, for example, LLVM, maybe for a reason, maybe because there is a common understanding that inline should inline function. It has some bigger threshold for the functions that are marked inline. In this example, you can see that function g inline was fully inline and called f several times, and they are just called. But g non-inline just has a call to g non-inline, and this has a separate logic. And I'm not lying. If I write inline in g non-inline, I believe everything will be inlined. Yes. So this example just shows that inline keyword matters in some sense, but that's also reflects your inlining. But that doesn't mean that you should write all your functions with inline. And actually, a lot of functions in C++ are implicitly inlined. For example, all class member functions are inline, all template functions are inline. And I believe this only helps for functions that are written in headers, which you probably shouldn't write and in headers. And the only thing that remains is like the source file where you do something in an anonymous namespace. But don't overexploit that. So that's just a fun fact that some engineers argue that inline has nothing to do with performance. However, it probably can have an effect. There's also a separate attribute called always inline, and this inline is the just marks, it's the compiler extension, and it marks that the functions should be inlined always. I saw some usages of that in weird places, in very like hot places. Be careful with that. So, but it can be used. I have an idea which I was not able to check on big scale, but on small scale it was working nicely. For example, just compile your project with inline threshold 1000 or 5000, wherever you prefer. Compare benchmarks and see what actually has been improved, or if nothing, then you're fine. If something has been improved, just put always inline attribute on the calls that were inlined with that threshold, and just have a clear win without binary increase. But that's an idea which probably has some sense. All right, I believe that we'll skip the function alignment. So briefly, I'll say about it. So sometimes due to microarchitectural reasons and some problems, you can commit code which have some benchmarks degrade in some other place, absolutely unrelated. And the reason behind that almost like usually is because of functional loop alignment. And what I want to tell here that sometimes it's better to align functions and branches. And for example, these two options helped us to reduce the variance of benchmarks and stabilize them, so we don't have any weird requests where some random code degrades the performance by 30% of a hot place. Yes, so they highly stabilize benchmarks at Google and at ClickHouse. I'll probably skip that a little bit just to take more questions. Standard library. This one I also want to talk about. So likely compilers come with standard library. GC has libstd++, Clang has libc++, MSC has its own standard library. And I believe the main difference is that of performance difference are in projects that actually using lots of, that are used a lot. For example, vectors, strings. For example, small string optimization size differs from library to library. In libc++ it's 22. In libstd C++ it's 16. In Facebook library it's 23. And in MSC it's also, I believe, 16. Some libraries use cow string, like copy and write strings and so on. Vector string resizing policy also matters there. Probably some unordered containers and a couple of functions like std sort or something like that. So, but probably the biggest difference that I saw that actually caught my eye is the additional options that these libraries have. And for example, libc++ has the option called unstable ABI. And now we are going into a very, very controversial topic about ABI. But for example, if you build everything from source, you can allow to use this option. You can allow yourself to use this option. And unstable ABI actually improves the performance of lots of things. For example, it improves the string optimization for some assignments. It improves actually the unique pointer. And it improves the unique pointer in a way that probably some of you know, but let me address this. So like on the left, just simple function G, which calls F and moves unique pointer. And unfortunately, due to Itanium ABI on x86, if the object is not trivially destructible, you need to store it in a pointer. And you can see that like this thing actually does something with the pointer dereference and so on. So that's not very good. And that just increases the code and some CPU cycles. However, if you use a trivial ABI, the difference is that the call is responsible for destroying. I believe there almost has been no breakages at Google when we tried that option. So it just forwards the call to F. And it removes all these unnecessary instructions that are not that should not be used. So let me get back. Yes, for example, at Google, we saw around 2% build size win from enabling this unstable ABI option just to remove the overhead of pointers. But it requires building from source. If you can't allow that, then don't listen to me. So. Standard also progresses. For example, C++20 has char-AT. It's one of the best features for performance. The difference between char and char-AT is that char-AT cannot overlap with any other data, whereas char pointers to char can. And we saw some good significant gains out of that in ClickHouse, because ClickHouse is a column-based oriented system, and marking the columns with char-AT is quite desired. And for example, here was the loop. So it was doing some moves, and these two moves were used to avoid pointer aliasing. And they were just removed, and we got several queries with better performance. So in total, several points that this talk covered: visibility, optimization passes, microarchitecture, standard library, inlining. Inlining is more optional, but still it may be useful if you care about performance. What I haven't covered in this talk is profile-guided optimization, and what it tries to do, it just tries to collect the profiles and have better loop inline decisions for future compilations. Post-link optimizations, where you don't need to recompile anything, but just to rebuild the binary to build blocks together, which are executed quite frequently to avoid cache misses of code. So on new pass manager, it's default in Clang 13. That's why I decided not to cover it, but it's like better pass manager strategy in LLVM, and it affects mostly inlining and tooling. So Clang Tidy has a full thing dedicated to static analysis. And now let's come to the juiciest part, results. So Mozilla Firefox decided to move from GCC MSFC to Clang. It uses for release builds LTO, PGO. It used experimental new pass manager, but it's default in Clang 13. 5 to 7% win on their tests, on their user tests. Yes, and here is the mark that they actually tried GCC plus PGO, and they moved to Clang plus PGO plus LTO. Stockfish, chess-based engine. So it's like a chess engine. They use LTO, experimental new pass manager, options up to AVX 512, and they achieve parity performance LLVM and between GCC. They had 3% win or around 20 ELO points. Yannick search engine where I worked. We used microarchitectural SSE 4.2, FLTO equal thing because the project was big and had lots of legacy, AVX FMA for hot paths. We transitioned to libc++, moved from GCC, increased the inline threshold to 1000, 7% better average queue response time. And I mean, like there are lots of backends for search engine. That was a huge win. One trading company, which I once helped for some reason, just it was a talk with a friend, and they use LTO thing, March equals Haswell, and inline threshold 1000 for release builds. 4% faster strategy response. They dropped GCC in favor of LLVM, and this was, I actually see bias in trading companies that they prefer GCC because it's still faster, and I believe that's a questionable case right now, and you just need to preserve two compilers and to compare them from time to time. ClickHouse, probably, which I talked a lot in this there. So we transitioned from GCC to LLVM, Dash03, SSE 4.2, FLTO thing, transition to libc++, stable ABI, char-AT, function alignment. And we tried inline threshold, but we may reconsider. For now, we dropped it because of build size increase. 7 to 10% better query response, 12% binary size win. So that came from LTO thing because it removed the functions that were not used anywhere, and from unstable ABI, which decreased the overhead of smart pointers. Google's perspective, we run everything with Clang LLVM. We use thin LTO for release builds. For testing, we don't use LTO. PGO for highly important binaries, SSE 4.2 or Haswell if we can prove that it will be run on modern hardware. And recently we moved from libstd C++ to libc++. It's very hard to understand the savings, to be honest. I believe it was around 3 to 5, but that's really, really, really huge number. And yeah, from unique pointer optimization, we got 2% binary size win. And that's it. So I'm happy to take questions. What could be the reasons for LTO not to improve the performance? That's a good question. As I said, sometimes inlining is not very good. For example, it pollutes the instruction cache, and sometimes it's just good to call a function which is I don't know, of middle size or of middle to small size, and it's just going to be always into the cache. And if it's called from different places, it's actually better than it's inlined in these places. So I believe the answer is something like that. GCC has -f fed LTO objects, but it seems like Clang does not. Is it built into Clang's LTO? To be honest, I don't know. So unfortunately, let's follow up with this question. Like, I know, drop me an email or write me so I can look into it and ask appropriate people. Next question: is -w aggressive loop optimization same as loop optimization from GCC 12? What can we use to enable loop optimizations pre-GCC 12? Use -03, or there are some options. I have a link to the code, like in my slides. The namings of the specific options you can enable to enable the vectorization. W aggressive loop optimizations, I don't know. I actually think that when the option starts with W, it's a warning, but I might be mistaken. So the answer is just to look into code and adjust them. Could you comment on, next question from Rohit. Could you comment on what PGO, POJO, profile guided optimization in GCC is mimicked by Clang? And if you had any experience in your experiments or results, specifically about GCC plus PGO versus Clang plus PGO. As I said, Mozilla Firefox had really good experiments on trying GCC plus PGO versus Clang plus PGO, and Clang plus PGO actually won this competition. Other than that, I don't know real specifics or how PGO is different in Clang and GCC. Next question: is it enough to enable unique pointer optimization with just the libcpp ABI unstable define? I believe yes, but please read code. If define libcpp ABI unstable and or libcpp ABI version more or equal to. So I believe yes. So I believe this define should be enough to enable smart pointer optimization. Next question from Chirag. Opaque function calls could be assumed to be strict memory barriers at places. Is that a safe assumption to make? Does that no longer hold for LTO? I believe it holds for LTO, so LTO knows what should be a memory barrier or not if it's marked like that. So I believe even compilers have extensions on marking the function opaque or not. So but I may be mistaken. So I'm like, that's all I know. Next question from Nina. Is it better to use thin LTO or full-scale monolithic LTO? I've heard that monolithic LTO still generates faster code, although linking is much slower. General suggestion from me, if your code is small to middle size, I don't know, 25 lines, 1,000 lines of code is probably okay for LTO to handle. But still, your project may grow. You need to understand that. Unfortunately, LTO has some cap on its scalability, and thin LTO scales pretty widely. So I believe to several million lines of code, which is pretty hard to write. I believe only like several projects in the world hit that limit. So thin LTO is very good for scalability, and what I can suggest, just measure. We see sometimes that thin LTO is just better than LTO, but probably in most cases, I know like 70% cases, yeah, LTO like 0.5, 0.1% faster. So if that really matters to you, that's 1%, stick to LTO, but be aware that this may not be scalable in the future. I have no more open questions. I believe I will be in Gather Town after the end of the talk, so it will be in a couple of minutes. We are out of time. I believe that's it. Thank you for listening. Thank you for being here. And let's talk there.